also for their wonderful and deep mathematical contribution to the theory of nonlinear PDEs. We know each other for many years, especially because I was in Chile until recently. I work in Chile, but Laurent and Marie-François have a strong collaboration with mathematicians in Chile, and so probably we have known each other for 20-something years, maybe more. Okay, so what I would like to talk today about is on a parabolic problem. So it's the analysis. So this talk is along the lines of analysis of blow-up phenomena in parabolic PDEs. Let me tell you the object or the main object of study for me this time is this system. Okay, this is called the Keller-Segel system, or I should say it's a simplified version of the original Keller-Segel system, which also involves parabolic evolution for the two components. So, here it is a coupling of a parabolic equation, of a nonlinear heat equation, and simply an elliptic equation, which is just Poisson equation. Right? So, or you can interpret it simply as a scalar equation, a scalar nonlinear heat equation with a drift term, yeah, and this drift term is quadratic, right? And this V guy here is simply the Newtonian potential of fluid. So this is a quadratic contribution, yeah, and of non-local nature, of course. Okay, so this is a classical model. I mean, many people have studied it for something called chemiotaxis. Chemiotaxis corresponds to the motion or the evolution of the density of a population of bacteria. Say U represents here the population density of this bacteria in a region of the plane in this case. And this motion is driven by, as usual, say, as in the simplest possible model, just by diffusion. Okay? And in addition, bacteria have a preferred direction towards they want to move, which is regions of higher concentration of these of something called the chemoattractant, and the chemoattractant is a chemical produced at every point of the domain, and by each of the bacteria. So the total contribution of the chemoattractant concentration, say, at a certain point X is a sum of the individual contributions weighted in certain ways, and we choose this weight is simply the Newtonian potential for this purpose. Okay, so U is the population density, so it's a non-negative thing, and what I look for here is for positive solutions of this equation that I call Ks. Okay. So let me tell you or remind you, if you are familiar with it, some basic properties of this diffusion problem, of this nonlinear diffusion. Well, first of all, I mean, it's obvious, right? I mean, it can be written as a divergence of someone, okay? If the someone decays fast enough, okay, then what we will have formally, right, is conservation of mass, right? Simply by integrating this quantity, say, in the entire space, you get 0 for the right-hand side. This is the computation, right? So the integral over R2 is this boundary integral, or the limit of this boundary integrals, and if you have sufficient decay, you expect at least along sequences of capital R, then this is 0. Of course, this is no news, right? This is usual for heat equation, but we have a very interesting identity that makes it different, which is a second conservation law, right? For this diffusion. Let me call M this preserved mass, I assume that this mass is finite. We have this interesting identity. This identity says that the rate of production of the second moment of U, so which is this weighted integral for the density of mass, is equal to 4 times m and times this number 1 minus m over 8 pi. Just to keep in mind the connection with heat equation. If you make this computation for heat equation, you get exactly 4m. So you don't have this guy m over 2, m over 8 pi. Okay, let me tell you again, formally assuming that everything is regular and that has enough decay. Well, at least enough decay to make this integral finite, right? So this is what I should consider. Then, so I just test the equation against x squared, right? Then I get this integral on the right-hand side. I integrate by parts. Simply I pass the Laplacian to the x squared, and assuming that's okay, that the boundary terms go to 0. Let me tell you that in order for this integral to be finite, I need that u decays at least as 1 over x to power 4. It should decay actually faster than 1 over x to power 4. So when I pass the Laplacian to here, I get 4, right? And this is the origin of this 4m term, which is what happens also in heat equation. And then you have this this guy, which is a sort of Quoc-Hung type term. Well, in fact, if you compute it, you can make a direct formal computation of it simply by recalling what V was. V is this convolution, right? So if you compute the gradient of this convolution, you get directly this formula. However, by replacing exchanging the roles of x and y, you get that this guy is actually equal to this integral, and this integral is x, right? Because here I have precisely x minus y squared, so this goes away. This is 1, and this is simply the mass squared over 2 pi. Okay, this is simply that. And therefore, by adding the two contributions, the contribution of the diffusion and of the chemical reaction, and I get this identity. Okay. This integral, this identity is interesting. Let me tell you something it tells us about this diffusion. It tells us, for instance, that if m is small enough, okay, essentially if m is small enough, you think that this term is lower order, then essentially you get the same type of conservation as for heat equation. Of course, this is natural because the nonlinearity is quadratic, right? So we have heat equation plus something quadratic in the unknown. So this quantity, this rate is positive, it's constant and positive. So that means this second moment is simply measuring the spreading of it, right, of the population, which has conserved mass. And but something is happening with this spreading. In the case of small mass, say this rate is positive and it keeps diffusing, spreading by diffusion. And with this comparatively smaller competition. On the other hand, if m is large, it's precisely if m is bigger than 8 pi, look at what happens. This rate turns out to be negative. And if it is negative, that means that the second moment or this spreading is actually going down in time. And in fact, if we make the computation, what we have is this, integrating simply the differential identity, the identity, then we get this. So the second moment is equal to the initial second moment plus this guy. If this guy, if the mass is bigger than 8 pi, then this is negative. And then if you let t grow, this quantity, if defined, right, becomes eventually negative. But this is impossible because we are always talking here about positive solutions. So this is a contradiction. A contradiction with what? With assuming that U is defined and smooth for sufficiently large times. And in fact, if m is bigger than 8 pi, then necessarily this solution has to blow up in finite time. So if the mass is equal to 8 pi, on the other hand, is also interesting. It turns out that this spreading is constant, right? So there is conservation of the second moment. This never happens for linear diffusion, let's say, right? So you have the second moment conserved if the mass is this level that people usually call it the critical mass. And if m is less than a pi, well, it's the situation sort of like in heat equation. And the solution spreads or diffuses definitely, in fact, for all times. Something we know, in fact, is that if the mass is less than or equal to a pi, the solution exists classically, it's regular and exists classically at all times. Yeah. So this is one important fact. Another fact is that if the mass is less than a pi, in reality, U goes to 0 and spreads in a similar way, in exactly what heat equation does. And actually, the asymptotics or the precise asymptotics or the underlying subsimilar profiles have certain explicit equations, and these were studied by Blanchet, Dolbeau, Pertin in particular. There are other works about that too. And all this analysis apparently started with the work by Jagger and Lucas in the early 90s. Okay, now I go back to the fact that for when m is bigger than a pi, blow up is expected. Blow up happens, right? Something that is part of the folklore of this problem, which is rather old, is that blow up, if it happens, yeah, should happen by aggregation. So what is aggregation? Aggregation corresponds to the presence of small spots, yeah, of the density of U for this population density of U, in which you have a concentration phenomena, but preserving mass somehow. Okay, and in fact, what is expected, or what people expect, is that U concentrates and forms a set of Dirac masses with mass at least a pi. There is, this is known under certain conditions. Okay, in fact, there is a reference I mentioned here that is some work by Suzuki and collaborators. So anyway, concerning examples where this truly happens, okay, there is not so much in the literature. In fact, however, this analysis of finding these solutions with aggregation and with this and capturing their profiles, this starts with Herrero and Velázquez in '96, and then you have, say, in these papers, actually, the radially symmetric case is considered, and a solution that blows up exactly at the origin in the form of a Dirac delta after a finite time is constructed. Yeah. Raphael and Schweyer constructed again this radially symmetric solution, and with a different method, and they added the information of stability inside the radial class of the phenomenon, namely, okay, if you perturb a little bit the initial condition, then you still see blow up, of course, but you see blow up with the concentration happening very close to the same point and for a close time. Okay. Then we have this work by Collot, Gould, Masmoudi, and Van Tien in a very recent work in which another method of construction is used, and they are able to capture the, in addition, non-radial stability of the blow-up phenomenon, namely stability when you perturb by non-radial things, not just inside the radial class, and also deriving very precise asymptotics that were not present in the work of Raphael and Schweyer. Okay. There is a spectral gap estimate that is the key the key element, for the key linear element. Okay, so of course, if you are not completely familiar with this problem, however, you are familiar with something like the prescribed Gauss curvature, right? I mean, this quantity 8 pi sort of, right, recalls something, okay? Of course, something happens at 8 pi, right? Why 8 pi and not the 16 pi or something else? Okay? And here is one reason. The reason is that, let me explain in the following way. This equation, even though it doesn't look like, is a variational structure. Of course, you have the usual energy, right? The usual H1 energy, and you can think of heat equation, for instance, as an L2 gradient flow for the Dirichlet integral, right? Integral of gradient square. But you have other ways of producing Lyapunov functionals or variational structure. For heat equation, one is the entropy, yeah, which is the integral of U log U. And this guy has a similar feature, actually. You have an entropy which simply adds to the usual one, U log U. It just adds this non-local term, yeah? Laplacian inverse of U, which is the Newtonian potential of U. And this guy is a Lyapunov functional for this equation. And it turns out that if you compute the derivative, then you get this identity, and this is negative, okay? It's negative unless you are standing at something where this is 0, where this is constant, actually. This is constant precisely at the steady state of this, right? And so this only vanishes at steady states. So the energy, this entropy is strictly decreasing, except at steady states. And the equation for the steady states, if you call V equal to log of U, then it's precisely this, right? I mean, you want this constant. So when you apply Laplacian, yeah, you get Laplacian of this equal to 0, and that amounts to exactly this equation, which is just the usual Liouville equation, right? Familiar in geometry in particular. And as it is well known, right? Solutions with finite mass of this equation, finite mass meaning the right-hand side having finite integral, right? Finite L1 norm. All solutions of these equations are known. They are simply constituted by translations and scalings of a single object, which is this function U0, which is a function that is really symmetric, nice. And it goes to 0 as with power 4, 1 over x to power 4. Yeah, so this is something. And what happens? Okay, the mass of all these guys, I mean, is just 8 pi. Okay, so this is where the 8 pi comes from. In the following sense, that now we also have that the entropy, in fact, is the same for all these functions. And when lambda goes to 0, if you let lambda go to 0 in this scaling, of course, eventually what you see is like this concentrates with fixed mass around a single point site. Yeah. Okay, this is the way in which people expect that the blow up take place also in the time-dependent case. By the way, these functions lambda psi are the extremas for a Sobolev type inequality called the log HLS inequality. The log HLS inequality simply says this. It says that the minimizer of the entropy when you restrict yourself to functions with mass 8 pi is precisely the extremas of the U0 is an extrema. Is in fact all the extremas for this variational problem are these functions U that I told you about in the previous slide. Okay, so a discussion I wanted to make is that in a certain sense, the functional if of E loses the Palais-Mail condition. So there is a loss of components. The loss of components in what sense is that you have steady states for the say critical points, right? In a certain sense, for E, a class for which the energy is constant, okay, and their limit which is the limit as lambda goes to 0, does not exist. So this is the typical way in which loss of compactness happens in critical problems. Okay, this is a problem from the variational point of view, in the language of the calculus of variations. Okay, so this is what happens. So this is this corresponds to something called this scaling invariant phenomena, in which in the limit you see something that gets out of the energy space, is what is usually called bubbling phenomena, okay, or criticality. Okay, let me go to the case of the critical mass. The critical mass in the sense that when you have mass above 8 pi, you have blow up. When you have mass below 8 pi, you go to 0. Then the question is, well, what happens when the mass is exactly equal to 8 pi, which is the mass of the steady states? Of course, one possibility is that you actually approach a steady state, right, as time goes to infinity. Steady states are definitely solutions defined at all times, right? And you have these works by Blanchet, Carlena, and Carrillo, and then by Carlena and Figali, in which they proved something very interesting. They proved that the steady states, the family of steady states that I mentioned before, is actually attractive, okay? So what you have is asymptotic stability of the family of steady states. Yeah? And this is, so it's a type of orbital stability, okay? But it's asymptotic stability in the sense of orbital stability. And this is what is established here. Yeah? I would like to mention this work, which is a little later only, Gomez, Nagai, and Yamada. They constructed an interesting example, okay, of perturbations that do not have finite second moment. Okay, this is something I forgot to mention. The decay 1 over x to power 4, which is the decay of the steady states, is critical for the existence of the second moment. The second moment is integral of r squared, right? Say if you use it in polar coordinates, right? It's integral of x squared divided by x to power 4 times dx. But that integral is in radial coordinate, in polar coordinates, is integral of dr over r. So it diverges logarithmically. Right? So so this decay 1 over x to power 4 is critical for the existence of the second moment. This stability I'm talking about here is when you take finite second moment perturbations. And in this work, the perturbations, what they show is that if you violate that, okay, if you have the decay like 1 over x to power 4 in the initial condition, you may oscillate between two radially symmetric steady states. So somehow that phenomenon is possible. And now, in the case of finite second moment, on the other hand, finite second moment of the initial condition, okay, which excludes the steady states. Blanchet, Carrillo, and Masmoudi discovered, in fact, before this works, discovered that you have existence in infinite time, of course, but also a concentration phenomena in infinite time, namely aggregation in infinite time. Aggregation in what form? In fact, they found that the U happens to concentrate at the origin or at some point Q in this way. Okay, simply as a scaling of the fixed bell shape. Okay, forming a Dirac delta as time goes to infinity. Yeah. Okay, then there were some formal computations. These papers are formal analysis. Formally, it was found what lambda of t was. Yeah, in the previous paper that I mentioned, is perfectly non-radial, very general. They do not know what lambda of t is. Now, much more recently, in a paper, I think the preprint is 2017, but it appeared just last year, Gowland Masmoudi constructed a radial solution with the profile that I mentioned here. Yeah, this profile. And they found that phenomenon happening as confirming the formal computations, which tells us that lambda of t is comparable to 1 over square root of log of t. Actually, there is a constant. Okay, this one should be a positive constant. This is the type, what appears to be the generic behavior, okay, for blow up as time goes to infinity. And they also found, with their construction, stability of the phenomenon inside the radial class. Why? Because they base their analysis in certain spectral estimate, spectral gap estimate, which they knew to be that it was valid only in the radial case. And the full stability was left as an outstanding problem, okay? Stability with respect to non-radial perturbations. What I would like to do now, I would like to explain you more or less how the mechanism, sorry, I jumped the theorem. Okay, our result, okay, this is joint work with Juan Davila, Jean Dolbeau, and Monica Musso and Junchen Wei, which you can find in archive. Our result is the following. Our result is a construction of a solution with infinite time blow up, yeah, but with a construction that allowed us to obtain the stability claim. The stability claim, which is of course an important feature, is simply phrased as in the following way: if you consider perturbations with small in certain sense, okay, for this initial condition, for the initial condition that we construct, any small perturbation, radial or non-radial, then you will always see a blow-up phenomenon of this form at some point Q. Yeah, this is where lambda of t is of this sort. Maybe I should say a constant here. But this happens for all small perturbations. So all small perturbations that preserve mass and that have finite second moment. Yeah. So this is our result, and let me tell you how it goes. I mean, first of all, I would like to tell you why such a phenomenon should be true. Yeah, or to give you a feeling of why this should be true. Why do you have? Why? What I mean is why you have this concentration in infinite time phenomenon. Okay, let me consider the Keller-Segel operator, which is this nonlinear operator S of U, which is the diffusion, the entire equation. Okay, so what we are trying to solve is this equal to 0. And what I would like to find is a solution that behaves in this way. Say that I am inside the radially symmetric case just for simplicity. If I consider an initial condition which behaves like 1 over lambda square of U0 of y, where y is x over lambda, yeah, and lambda of t is a certain function that goes to 0, this is what I would like to find. And I would like to determine lambda of t so that this happens. Let me make the following answers for a solution of this problem. The answers that I make is essentially answers, I mean, for an approximation. Yeah? What I would like to find is a solution that lies somehow close to this guy, but cut off. Why do I cut it off far away? I cut it off far away because necessarily, in order to see this type of phenomenon, you have to have finite second moment, and U0 does not have finite second moment. Okay? And where do I make the cutoff? For convenience, I choose it. I choose the cutoff to be in around the self-similar region in which this equation essentially passes from the mixed nonlinear regime, okay, to simply a heat equation, yeah, some type of linear heat equation. So this is why I choose the cutoff to be made in the self-similar region, which is of course very big, right? And the cutoff is of course 1 up to here, and then up to where this is 1, and then when this is 2 or higher, this is 0. Yeah. Of course, I lose some mass, right, when I do that, because the mass of U0 over lambda squared is 8 pi. If I make the cutoff, I lose a little bit of mass, but I make it up. I make up that loss of mass with this constant alpha in order to keep the constraint 8 pi. Of course, if I don't keep the constraint 8 pi, I could go to 0, right? So what I would like to do now is, after I have this initial approximation, what I would like to show you is that if lambda is chosen to satisfy certain special relations, then you can find a correction to this main approximation, to this first approximation, which has the same form somehow, okay? It's a function of the scale variable y and time, and 1 over lambda squared. I choose it of this form, so it's a perturbation of the bubble, if you wish. And I look for a correction of the approximation of this form in such a way that the error of approximation is reduced. The error of approximation will be reduced, but only if lambda is conveniently chosen. Let me make a computation. Say if I call phi or curly phi, okay, of xt to be this guy. And I replace in the operator that I want to make 0. I make this Taylor expansion. Okay, this is L of u plus some linear operator in phi, which is the linearized operator for the equation around the first approximation. Capital U is the first approximation. This is the elliptic part of it, okay, and then corrected by the phi t term, and then something quadratic, elliptic and quadratic, yeah, and which I will ignore for the moment. Now, if you compute for this function, this operator here turns out to have an approximate form which is quite nice. It's lambda to minus 4 times this straight L operator, which is the linearized operator for the stationary Keller-Segel problem around the basic U0 bubble. Yeah? And this elliptic operator is this operator. It's a second order operator with a non-local term. Of course, this is hiding something, right? Because here I have Laplacian minus 1, and here I have Laplacian. So even though it doesn't look like, this is actually sort of a fourth order equation. Yeah? On the other hand, let me tell you what I want to do. What I would like to do is to reduce the error by canceling this part, yeah, with S of u at main order. And that when I measure it in the variable y, this operator is in the variable y. Let me remind you. And what I would like to solve is this equation. Yeah? A posteriori, after I do that, I will discover that the time-dependent part is in fact smaller. Okay, but please believe me this for the moment. Yeah? So what I would like to find more precisely is a perturbation that has finite second moment. Finite second moment meaning y to minus 4 minus sigma. That's y to cos infinity. And you know that satisfies this this elliptic problem. Now, this elliptic problem can be solved in the radially symmetric class, in fact, in an explicit way. If you make a computation that simply, direct computation, you see, first of all, that this operator in phi is a divergence form operator for this G, which is a non-linear, non-local linear thing, okay? This guy. If you compute, you simply find directly that the G is given by this formula, and this formula tells you that if this guy had this decay, then the decay of this will be y to minus 6. After that, when I want to find phi, right? Not just G, but the connection between phi and G is given by the linearized Liouville equation, which is this. And what do I need in order to have solvability, or in order to find a nice solution for this? What I need is that the right-hand side is orthogonal to the radial kernel. The radial kernel of this is well known, okay, it's an explicit function. In fact, this condition can be translated into simply saying that G is L2 orthogonal to Z0, where Z0 is this. What is this guy? This guy is actually, for the Keller-Segel equation, is the generator of the invariance and the scalings for the elliptic part, okay, of the Keller-Segel equation. Okay, and now I see what does this mean? Well, what this means, yeah, precisely say is the following. Yeah. So this condition, integral of G times Z0, if you make the computation simply, okay, you get that the integral of Z0 times G it's nothing but the integral of y squared times the right-hand side. So what do I need? I need that the second moment of the right-hand side of the equation, remember this is what I am solving. I am assuming that the mass is 0. If not, I don't have anything. But in addition, I need second moment of E equal to 0 in order to have a good solution. And then this is what I need, yeah? What I need in order to find a phi with enough decay and infinity, what I need is to have these two relations satisfied, the mass and the second moment equal to 0. Now I go back to the equation that I really wanted to solve. What I really wanted to solve is this, L0 phi plus the error multiplied by lambda to power 4. And what I would like to find is a solution that decays. Why do I want it to decay? Well, because I want finite second moment perturbations, first of all. But second, in order that in the remote regime, when y is extremely large, I don't want that this phi interferes with the equation. This is a local improvement. Far away is supposed to be negligible, its contribution, yeah? Okay, so in order to have this, what I need at main order satisfied are these two relations, mass equal to 0 and second moment equal to 0. Observe that I went back to the variable x here. Yeah? Okay, if you compute now S of u, S of u, I divide it in two terms, okay? I divide it into the time dependent part, the derivative in time, and the elliptic part. Well, first of all, it is clear that I have that the mass is 0. Why? Because the u has constant mass. Remember the alpha, remember this number alpha in the definition of u is in order to have 8 pi for the mass. So this guy is 0. Say the mass of this guy is 0. The mass of this is 0. If this has decay, right? Because it is a divergence. Okay, so we have this. On the other hand, using that the integral of u equals to 8 pi and the same argument that we use to compute, the same computation that we use to prove the second moment identity, right? And using the fact that the second moment is preserved for the Keller-Segel equation. Okay, this is what happens when you multiply this times x squared. When you multiply this by x squared and you use that integral of equals 8 pi, the integral of this is 0. The integral of this S2 guy is 0. And the integral of S1 x squared, well, is by definition this. It can be written in this way. Okay, so what do I need in order to have the second moment condition for the right-hand side of the elliptic equation? What I need is that this derivative is 0. In other words, I want is that the second moment of initial approximation should be constant. This is what I want. Now, if you compute, here I simply recall what the initial approximation was. This becomes this, okay? It's an identity, okay? And then if you use the second moment, I mean, u decays like 1 over r to power 4. So this integral is like the log of the upper limit. And you get precisely at main order this, lambda squared log of square root of t over lambda. In other words, what I want at main order is that this guy be constant. And this guy be constant means more or less that lambda of t is like this. So main order will be a constant over square root of log of t. Okay, so this is the formal argument this is a formal argument with which we can derive what lambda of t should be. Now, for the true proof, for the true construction, what do? We do something in a very similar spirit. What we do is to consider parameters lambda of t and alpha of t, which I will adjust, okay? I will not assume a priori that alpha of t is exactly the one making mass 8 pi for this guy, but I consider the same initial approximation, alpha lambda minus 2 times u0 x over lambda, same as before. I will call it also u of lambda alpha, why not? Okay, depends on lambda and alpha. And what I would like to find is a solution that has this one, this equal to the initial approximation as a small perturbation. And the small perturbation, I will take it as a correction to the bubble in the inner variable or the local variable, the blow up at the blow up region, x over lambda, same as before. But what I do with it is I cut it off in the same way that I cut off the bubble, okay? And I add something which is a function more naturally expressed as a function of x, which I call phi outer. The phi outer is something that reflects correctly, hopefully, what is happening far away, right? What is happening far away. Okay, so what is the spirit of the argument is simply that I will find equations, which is a system, actually, that I will impose in these functions phi inner and phi outer, expressing their respective variables, for which a system that I will be able to solve if lambda and alpha satisfy certain special relations. So what I impose is that this satisfies the following system. Yeah. So, okay, sorry, I will motivate you I will try to motivate you what the system is. The linear operator near the core, okay, of the is this operator straight L that I showed you before, but far away, I didn't discuss what it was. Far away, look at what it is. Far away, the operator, well, the full linearized operator is this, right? But observe the following. The gradient of u decays like 1 over x to power 5. So it decays very fast, okay? And multiplied by the gradient of, okay, Laplace inverse of the curly phi. May have some growth, maybe logarithmic, but it's nothing terrible, okay? So this guy decays fast. And in relative terms, it's smaller than this guy. The gradient of v is just 1 over r. So you see that this is 1 over r times gradient. It's like Laplace, this operator. I mean, has asymptotically the same scheme. In fact, the gradient of v is the gradient of a log, of 4 times log, more precisely. And what you have is this identity, these two identities. And what these two identities tell you is that the dominant part of this operator, when you are sufficiently far away, is from the origin, is this operator. It's just Laplacian plus this, which is approximated by this guy. And look at what this guy is. Okay, if I assume for the moment that this thing is they have radial symmetry, this is just two-dimensional, right? Laplacian plus this term, and that corresponds to this operator. And this operator is a 6-dimensional Laplacian. Okay, for instance, fundamental solution in R6 is 1 over R to power 4. Okay, so maybe this is telling us something, right? So the regime far away is in reality a heat equation, but which in the radially symmetric case corresponds to a 6D heat equation. Yeah, this is the outer equation. The outer problem has this form, and the inner equation has this form. The inner equation is more or less an equation that involves the same operator that I showed you before in the variable y. Yeah, and of course there is some coupling, right? So you have terms, a term like this in the right hand side that depends on the phi inner, and this one that depends on the phi outer. Well, more generally, depend on the two variables, but the dependence on the other variables, phi inner here and phi outer here, should be the smaller order. They are. Okay. Now, at main order, this G guy is the following thing. It has some error, okay, that depends on lambda and alpha. In fact, there is another term that is actually smaller. And this one is something due to you remember that the phi inner came with the cutoff eta. So when you compute Laplacian, you get these two guys here, yeah? Which is, look at what it is. This depends on phi inner, yeah? This term depends on phi inner, but only on its values around the self-similar region, which is the support of the gradient of eta, right? And then what do you get? What you get for the inner equation is something of the same type, okay? This is something depending on lambda dot times the generator of dilations, observe that. And plus this term. And this term depends on phi outer, it's a non-local operator, which is coupling the two things. But what is the situation that I would like? What I would like is to find a solution in a space where phi inner decays sufficiently fast. Why? Because I want that phi inner becomes small when you are here, you know, around the support of the Laplacian of eta or the gradient of eta. If I manage to stay there, yeah, I will manage to stay there under conditions very similar to the ones that I showed you before for the elliptic equation. The same as I use for Fredholm alternative. If I assume that this is 0, second moment of this guy is 0 and this is 0, then I will have the possibility to solve this equation for phi inner, you know, decaying fast. And if it is decaying fast, when I solve this equation, I get that phi outer is relatively small and then the coupling gets weak. Essentially, the two problems become uncoupled if I satisfy these two equations. So this is what I need. What I need is to construct a theory to invert the linearized equation. Yeah, the linearized equation. And the linearized operator where you have the time derivative term multiplied by lambda square. And you can do that, okay? You can construct, this is a big technical ingredient, you can actually construct an inverse for this. And these relations, in fact, amount to certain relations for lambda and alpha for which you solve, and you find more or less lambda of t as an alpha of t as in the previous formal computation, okay? This is more or less the argument. Okay, let me tell you that the method, or with the same method, we are also able to construct blow up in finite time. This is a new thing because the only examples known were radially symmetric, and what we can prove is that you can find solutions with blow up at multiple points. Yeah, I should mention that the radially symmetric case was studied by these authors, as I mentioned before. And in fact, you have some subtle thing concerning the value of this constant. Okay? You have a behavior which is, this is the self-similar rate. So this is a type 2 blow up. Okay? It's not self-similar. Yeah? So you have this correction to the self-similar rate. But this is the first example with higher mass, yeah, in which you show that there is blow up in several points. So this is what you have. The solution in this result goes to a linear combination, so to a sum of Dirac deltas, yeah, plus some small function. This is more or less the space in which we move, and then here is the theorem stated part of the theorem. Yeah. Sorry, there is something else. Okay, sorry, this is the one result, but then there is another possibility, which is that you get blow up at a single point, but with, you know, a superposition of bubbles of different rates. This is a possibility. Why not? And in fact, this is one possibility, or simply that you have bubbles of similar rate in which they collapse onto a single point, solutions that are not radially symmetric, of course. And this you can construct. This we construct. You can find a solution that has mass 8k pi in the limit as it goes to 0, which is also a new phenomenon. It's a new phenomenon, but not from the formal point of view. Of course, Velázquez is a very, very clever guy with his co-authors, Seki and Sugiyama, found formally this, and this is what we prove rigorously now, in which you have the centers, okay, the center of concentrations, you have these several bubbles, and the concentrations are in the vertices of a regular polynomial. And this regular polynomial satisfies these relations. This is something that comes from the analysis, and this is what we can find. Anyway, just very quickly, let me tell you that the type of argument that we used actually in these constructions had a I would say, nice success in analysis of the harmonic map from R2 into S2, which is one of these parabolic problems with critical gradient nonlinearity, okay? And which is this problem. It is this problem, but where U is vector value that has values in S2, yeah? In this case, you have a blow up in finite time. This is known for ages, actually, after some work by Struve in mid-80s. And however, for a very long time, examples have not been found. Except the only examples found have been in certain symmetry classes. Yeah. However, truly non-radial situations were completely obscured. People didn't really understand them well. And anyway, there are many names in this analysis, including Raphael and Schweyer, Popping, etc. Yeah, and what we found, yeah, is was something very interesting. What we found was that you have actually blow up. For instance, you have blow up at a single point for this problem, but the blow up is unstable. It's in fact codimension once unstable. And this is probably what made it difficult to capture. Yeah. And this was conjectured numerically, by the way, that instability. Anyway, I will not tell you much about the proof. Okay, just telling you that you can find a result with the same flavor, where this capital U, of course, is something else. Okay, it's the basic bubble, which is the corrotational one bubble for the harmonic map flow. But I better don't elaborate much on that. Perhaps just telling you at the end that the corresponding elliptic equations, if you want to do the formal argument that I showed you before for Keller-Segel, is for a system, is for this elliptic system. Phi is vector valued here. And you have a Fredholm alternative for it that you can work out. And the equations that you get, though, are, this is a constant, it doesn't matter what this is. This is a complex constant, and here the solution depends on certain parameters like the alpha and lambda, okay, as before. But the equation that drives that is non-local. It's not an ODE. Yeah, and this is something quite delicate of the problem. Say certain non-local character of the evolution problem, of the reduced problem. But you can find the nice rates also in this situation. Anyway, so I think I will stop here. So happy birthday, Marie-Françoise Laurent, and thank you very much for the invitation.